All right, so today we're going to talk about the ventricular system and barriers in the brain. And so we know from 326 that we use the ventricles, particularly in imaging and section, to identify where we are in the brain. So they're very useful landmarks. And of course, they're also clinically important because if there's an occlusion of CSF flow in the ventricles, we get hydrocephaly. And we've talked before about occlusion-based hydrocephaly earlier in your degree. Now we're going to talk, in addition, about a dysregulation-based hydrocephaly. So hydrocephaly due to an imbalance in production and absorption of CSF, which is another variety of hydrocephaly. And finally, we'll talk about the barrier systems of the brain. So these terms you hear a lot, particularly the blood-brain barrier, or the BBB. So we'll talk about that, as well as another functional and anatomical barrier, the blood-CSF barrier. And I know my timing's been a bit off on some of the videos, so I'm going to try to not edit and fix that. So we know that the ventricular system is a set of 4 interconnected ventricles, and they contain and produce the cerebrospinal fluid. Within each cerebral hemisphere is a large lateral ventricle. These ventricles communicate with the midline third ventricle of the dencephalon via an interventricular foramen. And there are 2 of them, so is the interventricular foramina. The eponym for that is the foramen of Monro, so those terms are interchangeable. Similarly, the third ventricle communicates with the fourth ventricle via a single cerebral aqueduct. So remember that there are paired interventricular foramina, but a single cerebral aqueduct on the midline, or the aqueduct of Sylvius. And then the fourth ventricle continues caudally as the central canal, which is what's shown over here in bright green, of the caudal medulla and the spinal cord. And so most of this is reviewed for everyone, a couple of reminders, and a bit more nomenclature. So, as I just said, what ventricles are in the ventricular system. I want to emphasize, however, that the lateral ventricles, it's good to look at a view like this, a coronal view, because that gives you a reminder of where supero-inferiorly everything is located in the brain. So the lateral ventricles, of course, are in the cerebrum, and they're contained, there's bits of lateral ventricles in all of the 4 major lobes. There's an anterior horn in the oh my goodness. An anterior horn in the frontal lobe, so it's also called the frontal horn. A posterior horn in the occipital lobe, the occipital horn. And finally, in the temporal lobe, you have the inferior or temporal horn. The parietal lobe just gets a little bit of the body of the lateral ventricles. The third ventricle, is right here, buried on the midline. The thalami are its walls, so it's in the diencephalon. The cerebral aqueduct travels through the midbrain and connects to the fourth ventricle at the level of the pons in the cerebellum. And so that's a reminder of what level everything is at. We often see this representation of the ventricular system. So if you flushed the CSF out and filled the ventricular system with polymer, this is what you get. And most of the information here, again, should be review for you, I hope. One thing we're going to focus on, we know that CSF largely moves with gravity, so it tends to sort of sink down. So some CSF that's produced in the lateral ventricles will eventually end up in the fourth ventricle. From the fourth ventricle, there are 2 ways to leave the ventricular system. One is descending into the central canal of the spinal cord, which is a portion of the ventricular system. And the other is to enter the subarachnoid space. So the subarachnoid space is connected to the ventricular system via openings in the fourth ventricle. So these foramina in the fourth ventricle admit CSF into the subarachnoid space, and any CSF that remains in the ventricular system drains into the central canal of the spinal cord. Now we know in a mid-sagittal section, we cannot see the lateral ventricles. What we can see is this thin membrane of septum pellucidum that separates the lateral ventricles on the midline. We're peering into the third ventricle here with the thalamic wall and the thalamic adhesion, the interthalamic adhesion, visible at the center of the cursor, and the fourth ventricle, which is bordered anteriorly by the pons and posteriorly by the cerebellum. Just as it's important to know where things are relative to the brain, it's sometimes helpful to remember what level everything is at relative to external landmarks. So if you go straight through your head, you can see that the fourth ventricle is roughly level with the bridge of your nose. And in turn, in lateral view, roughly level with the midpoint of your pinna, of your ear, your outer ear. The right between your eyes, that's the rostrocaudal or superior-inferior level, better, of the cerebral aqueduct. And so that just reminds you where these things sit in your head. We've already said this, they have horns, the lateral ventricles, that project into each of the lobes. And the volume of the ventricles increases with age. So as you age, your ventricular system grows, and that's likely at the expense of your cortex, which is shrinking. So there is some natural enlargement, particularly of the lateral ventricles with age, because there's more room for them to expand against a rapidly deteriorating brain. Very depressing. We'll skip over that thought. Each division of the CNS contains a portion of the ventricular system, and we've talked about that. Here, this is the foramen of Monro, which you'll recall is synonymous with, what's the foramen of Monro synonymous with? And the interventricular foramen. So foramen of Monro, interventricular foramen, and that connects, in this case, the left lateral ventricle to the third ventricle on the midline. So you can see this metal probe is in the foramen of Monro. Now the third ventricle, we've said, is a narrow space between the two thalami, and it has these little recesses in it. So this is sort of the shape of the third ventricle is described using these recesses. If you look at the center, the third ventricle admits the passage of the interthalamic adhesion, so there's a hole in the middle of the volume of the third ventricle. And there's also two anterior recesses or little divots and two posteriorly extending little divots. So the anterior ones work around the optic chiasm and the pituitary stalk, the pituitary gland. So you have the supra-optic recess and the infundibular recess. And then posteriorly, they're located, and I have a better sectional image of this, around the pineal gland. So you have a pineal recess posto-inferiorly and the suprapineal recess superiorly, posto-superiorly. You can see that here on imaging. So this is a CT image with contrast for CSF. And I'm telling you it's the CT image because I have a very bright skull, very dark air, hypodense in the nasal sinuses, and then I have sort of kind of crap resolution of the sulci gyri. So this is a CT. The supraoptic recess and the infundibular recess are visible here anteriorly, and the pineal recess is labeled posteriorly. And these are clinically important because you lose these recesses if the third ventricle is enlarged. So the third ventricle has room to expand, these recesses get, or rather the divots between them get punched out. And so that's a sign that there's third ventricle CSF accumulation. The fourth ventricle has a roof posteriorly and a floor anteriorly. So the roof of the, did I say third or fourth? The roof of the fourth ventricle is created by the cerebellum, and the floor is created by the pons. The caudal tip is where it merges into the fourth ventricle, and this point is known as the obex. So the obex is also the marker for the foramen magnum. So at this obex, which is the taper of the fourth ventricle, that is the dividing line between medulla, medulla, and spinal cord. And so it's kind of an imaginary line, but at the level of the foramen magnum is where the obex taper is, and that divides medulla rostrally from spinal cord caudally. There are 2 lateral apertures and 1 medial aperture, and both of those exit the fourth ventricle to let CSF pass from fourth ventricle into subarachnoid space. So they are labeled here, but this is not where they are. This label is actually the obex, but the foramen, there are 2 laterally, and Luska is, that's spelled wrong, but is laterally, and 1 magendi medially. And those apertures admit CSF to the subarachnoid space. And so here you're in a dorsal view and a posterior view, and you can see, I don't know if you can see in there or not, but in there, this opening out is the route of CSF passage out of the fourth ventricle posteriorly on the midline. And so that's where the opening is. This mid-sagittal section, mid-sagittal section is the one I wanted for illustrating the recesses of the fourth ventricle. And as I said before, that these recesses will swell if CSF accumulates in the third ventricle. And so you have an optic or supraoptic recess. Those terms are synonymous because it lies right above the optic chiasm. An infundibular recess, which lies immediately above or sometimes around the pituitary gland. A pineal recess. That's an interesting mistake. This should say suprapineal recess because it lies immediately above the pineal gland, and then we have the pineal recess immediately adjacent, or perhaps just a bit below the pineal gland. So suprapineal, suprapineal. Good. And because this section is almost right on the midline, we can see the cerebral aqueduct. So the spaces in this section, this thin slice of the brain, this thin sagittal slice of the brain, would be filled, the white spaces would be filled with CSF. Now, in the brain, a lot of structures have a C shape. And so they're wrapped together, overlying each other in this C shape. And the most dominant structures of the C, the most visible and the largest, are the lateral ventricles. And then other things are sort of embedded within them. So we'll use this diagram as and in the next slide and just make a couple of relations. So we've already looked at how it fits with the brain, which is shaded in behind these. And now we'll look at how the ventricular system fits in with C-shaped deep brain nuclei. And the most obvious nucleus is the caudate, right? So the caudate makes a C that's nestled infralaterally to most of the lateral ventricles, but that relationship switches to inframedially in the temporal horn, right? So what do I mean? So I mean here you can see the head of the caudate is nestled immediately lateral to the anterior horn of the ventricles. The bodies travel together around this C-shaped curve, and the tail of the caudate is medial to the temporal horn of the lateral ventricle. So they really fit nestled together in a C. And if you're a word kind of person, you can see that the head of the caudate lies adjacent to the head of the the anterior horn of the lateral ventricles lies adjacent to the head of the caudate. The bodies lie together, body of the caudate, body of the lateral ventricles, and the inferior horn lies adjacent to the tail of the caudate, but the head is slightly lateral and the tail is slightly medial to the ventricles. What other C-shaped structure do I want to, we haven't talked as much about. So we've talked about the thalamus, and the thalamus lies, if you look in lateral view, at the center of that C. So they both wrap around it, and then the thalamus is nestled in the middle. And the other, well, the corpus callosum, shown here in orange, is roughly C-shaped and lies superficial to all of those, and dorsal. While the opposite is true of the hippocampal formation. So here, traveling from the mammillary body all the way around to the fornix, that C is deep and medial to the lateral ventricles. So if we look sort of top down over here in dorsal view, we have corpus callosum, the white matter tract connecting the two cortices. Then we would hit lateral ventricle if we were drilling through. Then the caudate. And finally, deepest in there, the fornix, the projection from the mammillary body to the hippocampal formation, which is labeled on these diagrams in purple. So all of these things travel in a tight C formation. And this table, you don't have to memorize it, but you should have it for reference, right? It just gives you some relative landmarks in the brain, and you should be really familiar with all of these terms. A new term maybe for some people is the atrium or the trigone of the lateral ventricles. So this is where all of the parts of the ventricle converge. So it's kind of the between part, between the occipital horn, the inferior horn, and the body of the ventricle lies the atrium.